Work magic, please. I am one of the less competent people, technologically speaking, unfortunately, which it makes a lot of sense. Oh, I guess there's multiple versions. One is probably the iPad and one is the computer or something like this. Hello. Hi.
Hello.
How are you?
Good. How are you?
Let me figure out which of the two things are you going to use to share so that I can make you host and deal with all of that.
Yeah. Sorry. I somehow I signed up twice, but yeah. I don't know
No,
why.
don't worry. Well, at one of these things, I'll just make both of them. I mean, it'll be fine. Make
Mhm.
co-host. Yes.
Okay.
But
I'm
you.
able to share.
Oh, yeah.
It
Excuse
says
me.
I can share. It says I can share, which is good.
Okay, as long as everyone can share when it comes available, this will be fine. Uh, and I guess I will admit everybody into the thing, and then I will get rid of the waiting room so that people can join
Mhm.
the seminar appropriately. And we'll give people a couple of minutes. Are you ready to like figure out how to sort of uh, get the slides in? We'll start in a couple of minutes. The fact that I've been doing this for a full semester and this is still a technical issue is, indicative of my ability to organize things, but only so much you can ask from a person.
I'm sorry. It doesn't allow me to
Mm.
share yet.
Well, that's a problem. Let's see if we can fix that. What does it say when you try to share?
Mm. Yeah. Let me just try again. Yeah. Okay.
Ah, brilliant. Great.
No. Mhm.
Are you are you technically both at Barnard and Columbia? I never really know how that works with Barnard. It's one of those weird things where like I'm never really sure how to like properly announce.
I think it's formally yeah. I have appointment at Barnard, but it's like Barnard/Columbia. So yeah. So
Barnard/Columbia is good enough for
yeah.
me. I just want to make sure I'm not tripping on anybody's toes.
Yeah.
We're sort of accidentally doing a mini series on dimers because 2 weeks ago we had Nishant Ndagotia and Catherine Wolfram who also did sort of dimery things. So accidental mini series you guys are participating in. Thank you for your collaboration, your contributions to this mini series that we accidentally put together.
Did they talk about higher dimensional dimers?
So Nishant talked about 3 dimensions and Catherine talked about multinomial.
Mhm.
So the n goes to infinity limit in that kind of things where things become solvable in greater generality. So the answer is yes.
Okay. So do you see it full screen now? It's like
No, it was full screen a second ago and then it went back to this mode.
okay, yeah. Right. Okay, so I'll just get back to it.
Yeah, so I think that should work. Let me grab paper so I can take notes.
Okay. And yeah, if I scroll, it also works, right?
I feel like it's a good habit to always have paper around and talk so that you can remember the things that happened and not be. Are we on time? I guess so. Are you ready?
Yeah, I think so.
Brilliant. Okay. We'll officially start. Thank you everybody for coming to the last pair of talks for the One World Probability Seminar for this term. We are delighted to have Alisa Knizel from Barnard/Columbia, as I was told, who's going to talk about breaking universality in the first talk, and I believe Leo is going to pick up from there. So please take it away.
Okay, yeah, thank you very much for the invitation and yeah, the audience for coming. So I'm gonna report on our joint work with Leo, and like he would give like much more like of a technical overview of the work with the more details and also other things in his second talk, and I will provide the general introduction to the subject and our specific focus of our work, which is the breaking universality in dimer models with example of a random lozenge waterfall. Okay, yeah, please stop me if you have any questions. Right, so I will start, as I promised, with some very general background things, and the subject of the talk is about quite a canonical setup by now. The setup of random tilings of a hexagon drawn on a regular triangular lattice on a plane. So yeah, so here we have this triangles with that you see, and the tiling of a hexagon is formed by pairing two neighboring triangles together. So in this case, they are colored with the red, purple, and light yellow. So we organize this pairing between neighboring triangles. There are three ways to pair those. There are three colors correspondingly, and that forms a tiling of such a hexagon. So now we are interested in different probability measures on the set of all possible tilings of such a hexagon. And there are many different ways you can define those. We will talk about a specific a class of measures that possess extra algebraic structure, which I will talk more about which I will talk more in detail later on in the talk. But first of all, the overall form of the measure will be the following. So we will have a weight of the tiling, which is denoted by this omega and this curly tau, curly capital tau is the tiling. So the weight of the tiling will be proportional to in the way it's written, it will be just the product of the weights assigned to the vertical rhombi, which are represented by light yellow in the figure. So this is the weight of the tiling, and now the probability of a given tiling will be the weight of the tiling divided by this function z, which is the partition function. It depends on ABC, where ABC are the lengths of the sides of the hexagon. So now, why we would want this structure for the weight of the tiling? The thing is that if you there is another convenient way to think about tilings of the hexagon through its three-dimensional realization. So if you look at the picture of a tiling, there is a certain 3D shape which emerges if you think about it as a stack of unit cubes in the corner of the room. Then those yellow rhombi, they essentially are the tops of the corresponding unit cubes. And if you just remember the positions of those yellow tiles, then you would be able to recover the whole tiling. So imagine you just erase this purple and red colors and just leave all the yellow ones. Since you know that they're the tops of these stacks of cubes, you would immediately be able to reconstruct the whole tiling. So it's enough to know just their position. And again, for some algebraic purposes, it's convenient for us to organize the weight of the tiling as a product of the weights corresponding to those vertical, these tops of cubes, this yellow, light yellow rhombi. Okay, so now, in the simplest case, which is already very interesting and quite sophisticated from a probabilistic standpoint, when we just assign all the weights of this yellow rhombi to be 1, we obtain the uniform measure on the set of tilings. And remarkably, there's this like well-known McMahon formula for which explicitly gives us the total number of tilings as this product of fractions, which is super nice. And in the different deformations of the uniform measure, which we'll discuss in the talk, the similar nice closed algebraic formulas for the partition functions for the partition function will also be available, and that's like kind of like the indication of integrability of the model. So the idea that we would be able to effectively use algebraic formulas to study the corresponding model. Okay, so now if we look at a simulation of a typical tiling, when we have all this there are like two ways to think about it. Like either you think about the side of the hexagon growing to infinity, or like the step, so the side of the unit triangle going to 0, we see the following shape which emerges. So it's known as the limit shape, and we see here the following phenomena where the so-called liquid region emerges. So this circle area inside of the hexagon, where we see all different colors, all like 3 different colors, in this case, orange, green, and red, which are present. So this is a disordered region, which is in high contrast with the regions which are close to the corners of this hexagon, where we see so-called brick wall pattern, where only one color of lozenges is present, and they are called frozen region. So the curve that you see, which emerges between the frozen regions and the liquid one, is called the frozen boundary. In the case of the hexagon, like going to the pioneering work of Kohn-Larsen and Propp, and then Kenyon as well, it was shown that, in this case of the hexagon, it is a unit circle, which is the frozen boundary, and like what you have inside is the liquid region, what you have outside is the frozen one. For more general domains were also studied in this context. Again, like the setup is that you draw the corresponding domain on the regular triangular lattice, and you send the sides of the domain proportionally to some number n to infinity, and look at the typical tiling of the corresponding shape, and you see a very similar phenomena present, which constitutes of this large liquid region, the disordered region where all possible colors, all possible lozenges are present, and the frozen region next to the boundary of the domain. Right, and you can look at even like more sophisticated domains where like this, so this like a Halloween picture, where you insert, where the original domain has holes in it, and still you would observe a similar phenomenon. Okay, so like formally, this statement about the limit shape is the convergence in probability of the so-called height function, which is noted by h here, to the limit as the parameter L goes to infinity, and here L times psi and L times gamma are the coordinates of a point inside the domain. So the height function, if we just go back to this 3D realization of the hexagon, so the height function is these numbers that you see. So so like when you look at the nodes inside the domain, so like the vertices of the corresponding rhombi, if you think about this tiling as a 3D picture with the stack of unit cubes, then the corresponding height of every vertex of the tile is just the height over the floor level. So if we think about this like bottom as as the floor, 0 level, then all the first level of yellow rhombi, they will all have height 1. Then if we move up, it's height 2. We move further up, it's height 3. So that's how the height function is defined. And so the statement about the limit of the corresponding function is the limit shape theorem in this context. So now one can look at different deformations of the uniform measure following the same setup. So we have that the probability of a tiling is the ratio of the weight of the tiling and the partition function. So here, like one way to deform this measure is through introducing a parameter q between 0 and 1, and then weighting every yellow rhombi in this picture as q raised to the power negative j, where j is the corresponding coordinate, so the like height of this, or like height of the corresponding if we like introduce like certain coordinate system, like j is the height of the like top vertex of the lozenge in the corresponding coordinate system. If one now looks at the product of the weights of all yellow rhombi, then it happens that this product is proportional to q to the minus volume, where volume here means just the number of unit cubes which are stacked in this like 3D interpretation of the tiling. Again, this fact follows from the combinatorial consideration that we just discussed, that every yellow lozenge is essentially just the kind of like the top of a stack of unit cubes. So if we multiply all these weights, we essentially just consider like all the kind of like heights of the stacks of unit cubes all together, and then like there's like some constant which just depends on the lengths of the sides of the hexagon. Okay, and so it's like the deformation of the uniform measure with one parameter. And again, if like for this deformation, there is a nice closed formula for the partition function which is available. And then one can perform a second level of deformation now with two parameters. So the second parameter is called kappa, where the weight of the yellow lozenge has like this quite peculiar form. And parameter kappa is actually, it can be an imaginary number with a certain restriction coming of some technical restrictions coming from the fact that like in the end we want to get a probability measure, and this restriction comes only from the given lengths of the sides of the hexagon. Okay, so again, the motivation for this deformation, so it can be viewed as a sort of like interpolation between the regimes where you look at the Q volume and Q minus volume case. So, and like another motivation for this consideration of the particular deformation is like through the fact that quite surprisingly, originally for this deformation, there's a very nice closed formula for the partition function. So this measure and like the corresponding computation of partition function was done in the work by Bordin-Gorin and Rains back in 2009. Okay, so for both these types of deformations, if one looks at the typical tiling of the hexagon, again, where the sides of the hexagon are scaled linearly with some parameter L, which tends to infinity, and parameter Q tends to 1, one observes a very similar physical phenomena where we see a large distorted region inside the liquid region and then frozen regions next to the boundary of the domain. So for the now I will just provide a very general overview of the results and questions that people studied for the uniform case and similarly for the presented deformations. So there are like the following. By now there's a very complete picture of different limiting properties for the tilings of a hexagon and more like general domains as well. For both triangle lattice and also there's a similar story about the domino tilings where one considers regions drawn on regular square lattices. So so there are like results available about the global limit, the global limit shape. So this statement about the convergence of the scaled height function. Then the results about the fluctuations of the height function. So the fluctuations are governed by the Gaussian free field. Then there are like many questions regarding the local behavior. So the bulk limit, so inside the domain is governed by the unique translation invariant ergodic measure, ergodic Gibbs measure. So that's like kind of like a generalization of the uniform measure, and which is translation invariant and ergodic in this case. Then there are results about projections to the sections in the bulk. So like once we look at particular like cross section of the like liquid region, there's a very concrete description of the correlations and the corresponding behavior on a slice. So and like it was like done in the sort of like period like the first like the last like 25 years all those results emerged. For the this deformed case of the Q volume case, or like this general two-parameter case, which is also called Q-Rakai case. I will explain this connection a little bit later in the talk. Similar results when the kappa is fixed and say like Q goes to 1. Similar results became available for the case of the like Q-Rakai. The focus is mostly on the hexagon region, and for Q volume cases for more general class of regions as well. And the like general lookout like outlook of those results is very similar. So there's a formation of the global limit shape. The fluctuations are governed again by the Gaussian free field. So the bulk limit is given by translation invariant ergodic measure, and the the projection on the slice is governed by the sign by the discrete sign kernel, and there are formulas for correlations as well. Okay, so now like going more into what our like work with Leo was concerned with, we want to look at a different type of the limit regime, where now we fix parameter Q and we don't send it to 1. compared to the previous slide, where all the results essentially recovered the same structure as one observes for the uniform case. So now, if we just look at the situation where, for one parameter deformation for the Q volume case and fixed Q, we see that there's essentially nothing interesting happening. The hexagon limit shape degenerates into this we call it Y shape. So there are just these three frozen regions that are sort of determined by the just the angles, just the position of those regions relative to the triangular lattice. So the corresponding the corresponding frozen regions would be covered by this brick wall pattern with just one type of lozenges. However, if one looks at this two-parameter deformation, when the parameter kappa is imaginary, there is something very interesting which happens, and it was first observed in this pioneering work by Borden, Gorin, and Rains via simulations. One observes a very different limiting behavior, which we see in the picture on the left. So here on this slide, we have a comparison between two limit regimes. So for the right picture, it's where this parameter Q is is sent to 1, and on the left it's where Q is fixed, kappa and kappa is imaginary. We see the formation of this we call this picture originally it was called the waterfall, because you can think about it as sort of water dropping from, if you sort of rotate it a little bit. Looks like water dropping from the cliff, and you have a very interesting sort of one-dimensional type a structure present in this picture, and that's exactly what constitutes this the collapse of the two-dimensional Gibbs structure into something quite degenerate, which we wanted to study in much more detail with Leo, and that's the essence of our joint work. Okay, so in order to formally introduce...
I'm sorry to interrupt. Can I ask you a question?
Yeah.
How should I think of these imaginary kappa weight? Because you told me that essentially these are real. This is still a probability measure, correct? This is not complex valued.
Yes. Yeah.
So just because I'm too slow to actually do the math real time to sort of understand what these kind of weights look like, what do they look like? Because there are negative numbers floating around and I'm a bit scared.
So the idea is that compared to this measure, when you introduce two parameters, now the total weight of the tiling is not anymore now depends on the actual geometry, the positions of the yellow tilings in much what I'm trying to say is that here, the overall weight of the tiling is just proportional to Q to the minus volume. So it's volume is some macroscopic parameter of a given tiling. Here, when you look at the corresponding weight of the tiling, actually the specifics of the geometry, the locations of the tiles, will now matter, and that's something which is reflected by this presence of the waterfall in the limit. like compared to like this kind of like more like global weight. When you like think about the actual, like values that you get for the like weights of the tiling, like what you would see is that right, like sort of if you have tiles like more like if you sort of like fix the like this orientation of your hexagon, if you have like more yellow tiles like present like further up the picture, the corresponding weight of the tiling will be larger. So there's like certain
so the monotonicity, if you will, still goes the same way of sort of wanting to increase volume, but it's a more sophisticated geometric thing.
It's still like a more like sophisticated geometric thing, right? The like again, like the details, like why the weight looks this way is more like ad hoc, meaning that it's it comes like very naturally from the like algebra, which I will talk about in the end of the talk, like where it doesn't like really have a very good intuitive explanation why you would want to consider this ways. It's like rather the fact that it comes with a certain like algebra, which is inherent in this in the process of the study of these tilings, and this two-parameter generalization has an interesting kind of like physical interpretation and counterpart to it. That's like the motivation to study it.
Right, thank you.
Mm-hmm.
Just one other thing, just real fast, is like, is Q smaller than 1 meaningful, or is it Q larger than 1 the same, just flipping everything?
It's not really meaningful. It's really
cool. Thank you very much.
It's the flip. Mm-hmm. It's the flip. Right. Okay. Okay. So now about the algebra of the things and how to formally introduce this waterfall region. So yeah, like again, like going back to the tiling model. So we have this regular triangular lattice, and the tilings formed by gluing two neighboring triangles together, where in this picture it's sort of reinforced by having these bonds between triangles. And I also have here this coordinate system INJ, and this coordinate this vertical coordinate J of the corresponding yellow rhombi will be present in the computation of the weights. So now we will discuss the following combinatorial interpretation of the tiling through an ensemble of non-intersecting paths. So it's another way to look at the tiling. Well, essentially just a certain affine transformation of the domain, like where you sort of like just shift the hexagon to the right. So instead of having this pink rhombi, you kind of like you squeeze it a little bit and tilt. You squeeze the yellow ones into squares and the purple ones into like this hexagon, right? Or sorry, parallelogram. So this particular shape, and so again, it's nothing more than just an affine transformation, which brings the hexagon, which we had like drawn on regular triangle lattice, into this form. So like where you have like the like vertical, like two sides of the hexagon are parallel to the like vertical line, and two sides of the hexagon are parallel to the horizontal line. Okay, so now if one does the following, inside all the square rhombi, one draws a midline. And also inside all the all the rhombi which came from pink tiles, we also draw a midline. Then it turns out that all those midlines, they will fit together into non-intersecting paths from the left vertical side of the hexagon to the right vertical side of the hexagon. And what one can do is one can look at the slice of this picture, and the intersection points are those yellow nodes that I have in the picture, and we have an induced process. So if we consider the like the probability measure on the set of all tilings, we get a probability measure on the configurations of these nodes, which are intersection or of the section with the non-intersecting paths, for like we get a measure on the like all possible configuration of that intersection points, essentially. Okay, so like our like waterfall in this transformed region looks like this. So now we just like have kind of like the alignment of the like this waterfalling with our vertical direction, and yeah, that's how it looks. So the position of this region is determined by the sides of the hexagon, which I will discuss next. Okay, so yeah, like that's how it looks. Again, this is like the midline of our transformed hexagon, and that's like the parallelogram where the waterfall region will occur. So like one of the statements that we prove with Leo, which Leo will talk more about, is the following statement about the concentration of these non-intersecting paths inside the waterfall region. The exponential concentration. So the formal statement we have here. So the probability to find like this like hole meaning like this kind of like missing. Yeah, so if we look at this picture, like with this slice, the hole corresponds to the like rhombi which we have between the nodes. So yeah, which kind of like misses the presence of the path inside it. Right, so we have this concentration result. And like also we focus on the study of what's going on for like a given slice of the waterfall region, which we yeah, so yeah, like if we zoom in, it looks like this, which reminds the barcode, and that's how we address it. Yeah, and the statement is that yeah, so the correlations on the slides are explicit and are not described by a discrete sign process compared to what one expects and like one get for the uniform case, or this like case where you have Q to the volume measure. So yeah, I should have put like a star next to this theorem, because yeah, like what we do is we numerically check that it's not governed by a discrete sign process, and like give some ad hoc arguments, but it's something which is still like work in progress to get an explicit rigorous explicit description of the corresponding like process. So we have conjectured formulas here. So there should be like a star next to this theorem. Okay, so like overall, the content of the paper is the like yeah, like this law of Flash numbers and the concentration phenomena, then the conjecture about explicit formulas for the correlation kernel of this one-dimensional barcode process. Yeah, so we also conjecture the exponential decay of the correlations, and like we support all those conjectures by extensive numerical evidence. So that's hopefully some future work which will be coming. Okay, so and finally, like before I pass to like the talk to Leo, I will set some background for the discussion of the like methods and the algebraic origin of the model, discussing the like classical setup for the study of dimer models, yeah, like which goes back to the 60s of the last century. So right, okay, so like one of the yeah, so the fundamental object here is the so-called dimer covering of a bipartite graph which is a subset of edges which covers every vertex exactly once. So here, we have a picture of the graph with pink nodes. Now, if we think about all the edges of this graph to be either this solid blue lines or this punctured pink ones, then this collection of the blue edges would be the dimer covering, because again, it covers all the nodes, and there does it precisely once. So now, for every if we fix a graph and consider the set of dimer coverings, there's a corresponding construction of the probability measure on the set of dimer coverings, which resembles the one that we used for the tilings. So the weight of the dimer is the product of the weights of all edges present in the corresponding dimer covering. And the probability of a given dimer covering is the ratio of the weight and the partition function. So now, the correspondence between the tilings of a domain drawn on a regular triangle lattice and certain dimer coverings goes as follows. So if we look at the, if we fix our domain and look at the graph which is constructed by putting nodes in every triangle which is inside our domain, and then connecting the nodes by an edge if the corresponding triangles are neighboring inside the domain, we get the following partial hexagonal, essentially just a part of hexagonal lattice which is enclosed in our domain. Then we can think about the pairing between the triangles which constitute the tiling as pairings between the nodes of the underlying underlying graph, and this pairing it gives us the dimer covering of the corresponding graph. So essentially, it's a bijection between the tiling of a domain and dimer coverings of the underlying graph. And therefore, this resemblance between the way in statistical physics the measure on dimer coverings is organized and the way we introduce the measure for the tilings of a hexagon that we studied. So now, in order to effectively study the probability measure on the set of dimer coverings, one needs the following tool, which is which is present in the original work from the 60s by Knizel, Tepperley, and Fisher. So it's called Knizel, Tepperley, Fisher theory. So it's the way to compute different properties of dimer covering using linear algebra. So the idea is that one defines a matrix A, which is called also a Knizel matrix, in the following way. So the rows of this matrix, they correspond right. So if we fix a graph here, and for this particular graph that we have in question, we can also it's a bipartite graph, meaning that you can color the nodes into by say black and white in such a way that only vertices with different colors may be connected. So it never happens that black is connected to black or white is connected to white. Then we can think about the rows and columns of the sketchline matrix as being labeled by the corresponding black vertices and white vertices. And the entry of this matrix is given by the weight of the edge of if it's present between the corresponding vertices, or it's 0 if there is no edge between B and W. So now this like weight between the vertices is it depends on a given orientation of the graph. So for any, the orientation is just the way to assign like arrows on all the edges of the graph. So if you fix the assignment of arrows and then use this procedure, you can construct a matrix A. So now this matrix is called cache lane matrix if the underlying orientation that we used is the so-called cache lane orientation, which is the orientation that assures that the number of the overall the difference between the edges going from black to white or vice versa over any face on a graph is the same. So that's something which is called the cache lane orientation. If we start with it and then construct a matrix, then it's called a cache lane matrix. There's a statement behind the scenes that a cache lane matrix, the cache lane orientation always exists for such a bipartite planar graph. So now the main statement is that for this orientation, one can compute the partition function for the graph. So this sum over the weights of sum over all possible dimer configurations of the weights of the corresponding dimer configuration as the absolute value of the determinant of this matrix A. Just to sum up, we take a bipartite graph on a plane, like a planar bipartite graph. There's a process to find this orientation. Again, it needs to satisfy this property about the number of edges going in different directions, counterclockwise or clockwise over every face. So if we assign those orientations on the edges according to this cache lane orientation, then the partition function is computed as determinant. So that's a very big deal, because now you sort of put the combinatorial combinatorial questions that in the end determine the probabilistic aspects for the corresponding model in the linear algebra setup, which is a big step for the computational purposes. Okay, and moreover, again, if we just as a direct corollary, essentially from this theorem, if we fix any set of edges within our graph, we can compute the probability that the corresponding set of edges occur in a given dimer covering as again as a certain algebraic expression involving now the inverse cache lane matrix, so A inverse. So that's just to sort of highlight the power of this approach when you translated the computer question into the linear algebra realm. Okay, so now back to our setup with the shifted hexagon and the corresponding tilings. So again, we look at this process which the induced process on the intersection point between the section and the ensemble of non-crossing paths. And one of the kind of key statements that allows the authors to study like many questions about the tilings is the following statement that the probability of observing a particular configuration at a slice like labeled with the coordinate t is proportional to the following quantity, which is like a product of the weights assigned to every location of a node. So this weight is explicit. It's given by like one of the classical orthogonal ensembles. In this case of the Q volume, it's given by Q-Han ensemble. And then like we have this product of the difference of Q raised to the corresponding coordinates squared. So essentially it's sort of like a deformed log gas ensemble where instead of just the difference between locations of nodes, xi minus xj, we have the difference for the corresponding Q weighted coordinates. Right, and for like this more complicated ensemble, like that we are interested in the Q, like the doubly deformed, like uniform measure with parameters Q and kappa. The similar statement holds, where again the probability of a fixed configuration is given by like a deformed log gas ensemble, where now the coordinates where now the deformation for the corresponding coordinates is like has this like form. Okay. And the weight function here is again explicit, and it's known as the weight function for the Kuraka ensemble. Like this is like one of the like classical orthogonal ensembles, and it sits in the top of the so-called ASCII scheme of orthogonal polynomials. So that's like where the origin of the algebraic appeal for this deformed measure comes from, and like also like explains this name that I've used prior, the Kuraka measure. So it comes from this result about the like process that we observe on a slice on the vertical slice of the picture. Okay, so like this result allows like one to compute the correlation kernel for the model, like using the cache line like theory that I have just introduced, and like we can also like use it to compute this inverse cache line matrix, and like just like as a like very like rough sketch of the proof strategy for like all these models like uniform, Q deformed, and like doubly deformed measure. Like one way to approach those questions is like through this like three steps. One computes the inverse cache line matrix and studies the limit of this matrix. Yeah, and this is the like the general scheme that we also take to address this question. So this idea of how to execute it goes back to the work of Borodin and Olshansky. Right, and that gives us the power to establish like what I have introduced and announced as our main accomplishment, the conjecture about the explicit correlation kernel of the model, and statements, like again, like the conjectural statements about the decay of correlations in our limit regime with the waterfall present. Okay, so like that's the summary of the approach. So again, like we use this like classical approach with the like cache line theory, and then combine it with the algebraic structure which is present in our model in order, and then study the limit of those formulas to obtain the results about the special degenerate case for the tilings models that happens specifically. Let me just go back to the main picture here, like the waterfall regime, when we observe something very drastically different to what one sees in a kind of conventional limit regime, when everything looks much more symmetric, and specifically you get the translation invariant to dimensional structure, local structure in the limit. Okay, so let me stop here and ask if there are any questions. Otherwise, Leo will get we'll show you more details and more explicit discussion about the formulas that we get. Mm-hmm.
Thank you very much. Everybody applaud at home, wherever you are, please. It was a lovely talk. If there are any questions, please feel free. At least someone is playing along with me. I appreciate it, Leo. If there are any questions, please feel free to unmute yourself or ask in chat, and I will read them out loud.
May I ask shortly? Thank you. It was interesting. Just two questions, general ones. Firstly, is this in any way connected to random tessellations? You mentioned tilings. You are not an expert in dimer model. And shortly, secondly, how extensive is this in terms of random ensembles, random matrices? What kind of ensembles, apart from the GOE, I think that you had, could you get? Thank you.
Thank you very much for the question. So I think when you talk about random tessellation, so usually it's the question about the whole space. Here, in terms of the subject, it's still quite specific to some to the domains or to finite size domains on the plane, and you have a very regular type of tilings of those domains. So it's either the dominos when you talk about this square grid, or rhombi when you talk about the triangular lattice, which is kind of the underneath your picture. So for the tessellation, it's so the questions that I've usually seen in the literature, so it's some specific so people are interested in tessellations of the whole plane, and usually there are quite peculiar type of tiles that people prefer to use, right? So in this regard, it's quite different matter. So the kind of the geometric premises similar, but what one observes in terms of in terms of this limit shape phenomena and other features are quite specific to the situation that we are dealing with here. So I don't really know any other setup where you get something similar, probabilistically, that people look at. Maybe somebody can correct me. But I haven't seen. And regarding your second question, when you when we talk specifically again about this model, there are different type of orthogonal ensembles that show up in this story, and those ensembles, they they are members of this ASCII scheme of classical orthogonal ensembles, and they sort of they also are related to different matrix models. There's there's no really very specific connection that you can pinpoint between the tilings and the random matrices, but there are many similarities. So say there are different models in matrix theory, asymptotic matrix theory, where similar, you can find similar orthogonal polynomials, and just similar idea that log gases very naturally appear in the study of random matrices. Or another place where random matrices appear in this picture is when you talk about fluctuations near the boundary, near this frozen curve that separates the liquid region with the frozen one. In this classical setup, with uniform measure and the Q volume, like it's known that it is governed by the so-called GUE minor process. So again, like something which pops up in the random matrix theory. Okay, I hope that answers your question.
Yes, clearly. Thanks.
I would, can I add about random tessellations is that sometimes you can define dimer models on random graphs to an extent. And this has some similarities. And as I briefly Googled random tessellations, these pictures have some similarities. And I'm going to talk about random dimer weights in half an hour.
Thanks.
If there are no further questions, we'll take Alisa one more time. Thank you very much. And I'm going to take a very quick break and let Leo set up and be back in a couple of minutes to start.
Okay, thanks. Thank you.
Very good question. Do you see my mouse pointer? No?
Yes.
Yes, thank you.
Is this a dark for everybody or just for me? Okay, great.
Sorry, I'm clicking a few buttons. I'm just
Too many buttons, too little time. I understand. It was more of a like trying to make sure.
It's not broken, I think.
Listen, I have an incredible capacity to break things via the internet. Anytime I get closer to any seminar situation, some level of technology breaks. I cannot tell you the number of times that we just check everything works out. The second we get into the colloquium room, suddenly the projector doesn't work, that kind of thing. That seems to be some aura I project, or I don't know.
Yeah. So if somebody's bored, you can open this QR code and have fun.
Well, now I want to open the QR code.
Yeah.
I don't think I'm going to be bored, but you know.
I'm going to put this in the chat as well.
Is this like a dynamic dimer thing you put together that we could look at see the pretty pictures?
Yeah.
Oh, lovely. Although you probably shouldn't have given me something fun to play with when I should be listening.
That's okay.
Oh, whoa, it's pretty.
Raises a bar for me to get people, not look at that and listen to.
I appreciate that. I appreciate when my speakers want a challenge. It's always good to have ambition. Boy.
Okay, I need one more thing. I think something is still not how I want it, because I want to see participants for some reason. Now, where is that thing? Okay, here it is. Okay. All right, so that is better. Okay. I just want to see my tiny window if possible, just in case. All right.
All good?
Yeah.
Okay. Welcome back, everybody, from that very long break. I hope, like, you feel refreshed and everything. And we'll have Leo Petrov from the University of Virginia for the second half. Please take it away.
Okay, thank you. Yeah, so I will talk about two things. Some things are broken already. Okay, restored. So I'm going to talk about two things, but let me quickly recap. So Alisa explained what the Curacao model on the hexagon is, and there are some results and there are some explicit conjectures that we have. And we didn't set out to work on, to formulate conjectures. We wanted to prove the waterfall behavior, which we proved at a large scale. We also wanted to compute the correlations in the waterfall. And we had all the ingredients, and we reused a lot of the formulas and techniques from old Castellan approach and the orthogonal polynomial ensemble structure that Borodin, Gorin, and Rains uncovered. And then you need to take a limit of very complicated formulas. And I'm going to show you how, what works, what doesn't work, and what exactly breaks in our approach to the conjecture. There are some other approaches to the conjecture that are also possible. And some things can still be done, I hope, but let's not get ahead. So it is very important to contrast two regimes. One is the classical regime when the parameter q goes to 1. That's when you have something that basically is locally behaving as if you took a uniformly random lozenge tiling, and there is a frozen regime or the waterfall regime when q is fixed, just like Lisa explained. Then the second half, so if I have time, I also want to completely shift to a different topic, not joined with Alisa, but with Alexei Bufetov and Panayotis Zographos on dimers in random environment with random weights. It's just that in the spirit of breaking universality of dimer models. So these are two things unrelated. Mostly my goal is to focus on the first part because that's where we have all the background and all the setup being done. So without further ado, I'm going to reparameterize a little bit of the weights so that they can emphasize the ingredients, which are showing you that really the Curacao model of lozenge tilings in the hexagon is somehow placing the lozenges in a double well potential. So what is double well is coming from is basically, so I'm picking kappa, I'm replacing kappa by chi, which is just a positive real, so that we're not thrown off by the negative kappa, where kappa is a purely imaginary number over here. And I also want to reshift everything to relate to the centered height. So in this case, height takes values in this particular hexagon. Height takes values from minus 2.5 to 2.5. And so the double well nature of the weights is basically that you are having one summand goes to infinity when h goes to when h becomes very negative, and then the other summand goes to infinity when h becomes very positive, and h lives on the order of the side of the side length of the hexagon, and so it scales to infinity. So basically the weights become exponentially large when horizontal lozenges, which is pale orange color here, when these horizontal lozenges are the further away from the center. So you want horizontal lozenges to escape away from the center, and that's where you get the waterfall regime when Q is fixed. Now, the classical regime, as Q goes to 1, and Q has to be scaled in this manner, they are present in the literature with different limit results. And somehow, and I'm going to explain how much easier it is to study that. I have to take a super quick break, otherwise my oven will keep ringing the whole time. So just 1 minute.
As much as we do love math talks, I think if something is on fire in the background, that seems like a good excuse.
Okay, there we go. Right. Is that pretty clear? And so basically what we have is as Alisa explained, I'm just kind of recapping what happens is that in the waterfall case, the horizontal lozenges, the pale orange ones, want to avoid the center as much as possible, so they concentrate into 2 plateaus. And if instead Q goes to 1, you get this kind of limit shape. So the difference between the two is that in the classical regime, or how do you recognize what happens? In the classical regime, there is a kind of a classification of what is possible to be seen locally. Like the only things you can see basically are either liquid or gas phases where all 3 types of lozenges are present. And the difference between the 2 regimes is the correlation decay. They look differently, but there are all 3 types of lozenges present. Or there are frozen regions, which are consisting of single color. Or there are also semi-frozen regions, which are, depending on the geometry, they would basically be looking like the waterfall. But in the waterfall, you see the sequence of colors is random. And in the semi-frozen regime, the sequence of colors will be, maybe 2 orange, 1 blue, 2 orange, 1 blue. So you will have a tilted wall, or maybe if it's a 45-degree wall, you get orange, blue, orange, blue, orange, blue, and that is regular. There is no randomness. So this kind of shows, and this result already that we proved shows that what we see locally is not from that classical classification of local phases in the Kenyon-Akonkov-Sheffield theory of random dimers. Okay, so now this is where it gets really technical and interesting. First of all, we are using, or one should use to study asymptotics. One should use determinantal structures. And a particular kind of determinantal process is the orthogonal polynomial ensemble, where you have the product of single term factors and also the interaction term, which is basically the square Vandermonde in these quadratic coordinates. And the single term look pretty bizarre. It has 4 q factorials on top, 4 q factorials at the bottom, plus some other factors, and then you have to change variables in the parameters so that they relate to the hexagon in this way. However, there is some kind of a advantage of this orthogonal polynomial ensemble structure, is that the correlation kernel is, if you interpret it as an operator in the L2 space, then it has this format. And this formula is very nice. It's an orthogonal projection operator in a basis that is hard. It's formed by orthonormal Q-Raka polynomials, which are Q hypergeometric functions. But conceptually, it's a Hilbert space with an orthogonal basis, and you have a spectral projection onto the first n eigenvectors. Moreover, it gets even better because the Q-Raka polynomials are coming from the hypergeometric family of orthogonal polynomials, which means that they satisfy 3 diagonal recursions, 3-term recursions, both in the n index and also in the x index. So this is the operator on top that is this operator is an eigenoperator, meaning it's diagonal in the orthonormal Curaca polynomials. And the coefficients of this operator are not as bad, let's say. So this W had, each W had 4 Q factorials on top, Q factorials at the bottom. But then you take the ratio of Q factorials, you get expressions which look like this, which are single factors, like single two-term things. And B and D are also coefficients that are present in some literature in orthogonal polynomials. You can pull it from there. They're also explicit expressions, though they also don't have Q factorials. They only have these rational factors. And so once you write down this operator, the correlation kernel, whose asymptotics we'd like to understand, is just a spectral projection onto the spectral interval associated to this tridiagonal operator. So this tridiagonal operator is a bounded operator in L2 space, and it has spectrum that's discrete. So we pull out a piece of the spectrum, and we say, well, we in the eigenbasis we just hit it with projections, meaning corresponding to the pieces of the spectrum. But the notion of a spectral projection of an operator is continuous. So if your operators converge, then under some conditions, spectral projections converge as well. And that's a very nice property. It's developed for when before the limit and after the limit, the operators are self-adjoint in the same Hilbert space. This idea was applied by Olshansky in context of similar to Losensteilings. And also Terry Tao applied it non-rigorously to random matrices, because in random matrices turns out that the Hilbert spaces before the limit and after the limit are different, and it hasn't been picked up over 15 years. So somehow there seem to be hard analytic troubles here. However, in the classical regime, when Q goes to 1, everything behaves nicely. So what happens when Q goes to 1? So basically Q is e to the constant divided by n. And then every piece of the factor like this, capital T, little x, everything like that just grows with n linearly. So when you raise Q to that power, you don't have to worry about anything. You just replace Q to the T by, e to the minus gamma T over n, and T over n converges to some, limiting T. So all the parameters are really just there, and this operator converges to a very simple operator. After removing common factors, this becomes just it becomes a translation invariant standard tridiagonal operator with an arbitrary constant. And the spectral projection associated to the limiting operator is simply the sign kernel, because you can pass to the Fourier space, and it's an exercise in simple Fourier analysis to reconstruct this formula. So this is the universal discrete sign kernel that you get in a vertical slice of a random tiling. So here's my random tiling. Here's what I'm slicing it by, and here's what the slice looks like. So what is this kernel describing? So this kernel is describing for me the correlations of, let's say, vertical steps in this. This is a downright path. It makes steps right and down. So the joint distribution of the down steps is described by this kernel. To be very precise, this curve, the section has a limit shape, and the limit shape is some continuous curve. And so this phi parameter depends on the slope of this curve. So basically you have to zoom in to the lattice scale and take a limit, and then you get correlations described by this discrete sign kernel, which is of course the discrete analog, discrete counterpart of the celebrated continuous sign kernel that appears in unitary symmetric random matrices in the bulk. Okay, so this is it for the classical case of the asymptotics. Now let me just give you a sample of a waterfall regime. So in the waterfall regime, the slice does this, and the correlations would be correlations of the down steps. But you see that in the waterfall regime, the whole drop here consists almost entirely of the down steps. So basically, the correlations will not be between 0 and 1, but rather in this region, the correlations would be exactly, you have every step is a down step. So the limiting kernel would not be that thing, but rather it would be the identity operator, right? Because all the correlations, so my formula for the correlations is here. All the correlations are going to be determinants of the same thing, but also on the other hand, all the correlations will be identically 1. Where here particles mean down steps. So this k should be the identity operator in the limit. So this is what happens here in the fixed Q regime. So it implies that we shouldn't be expecting the sign kernel. Rather, we have some kind of other limit that Alisa explained should be called the barcode kernel. Sorry, the barcode kernel would be something else, but in this cross section, in the vertical cross section of the waterfall, we actually would expect the kernel and the correlations to converge either to 0 or 1. I'm talking about local convergence, so it's not that as if I'd taken correlations between middle of the waterfall and a flat piece. Now these things become independent because they're far away in the system, so it doesn't matter. Like we really need to just look at joint correlations in a lattice scale somewhere along this curve. The most interesting situation is happening here around when the curve turns. So if you zoom in, if you like take this piece, it will be something very interesting. It's even harder to get there and understand anything even than in the case of the barcode that I'm going to talk about. And the reason for that is that as you take the limit of this three-diagonal operator and you have Q fixed, right? Remember that each of the factors here consists of a bunch of products of, Q to the infinity plus kappa squared times Q to the minus infinity, maybe, or something like that. So they scale, and there are about 10 factors on top and 10 factors at the bottom, that order of magnitude. And for each factor, when Q is fixed, for each factor, either the first summand in the factor dominates or the second summand dominates. So if I'm looking here, Q to the t can go to 0, and then Q to the x can go to infinity. Or you have to remove the common factor. So it's basically x minus t maybe. So then x minus t could be positive, then this thing doesn't matter, and you replace the whole bracket by 1. Or x minus t is negative, it means that this goes to negative infinity, which means that 1 here will be negligible, so you have to replace the whole bracket by the second term. And depending on where you are in the system, you will have to really deal with a lot of case-by-case analysis. So we identified 7 different cases as you go along the cross-section, the top piece, the transition, the top half of the waterfall, the center of the waterfall is a different thing. And then the bottom half of the waterfall is when Q goes to Q inverse, essentially. And then, the rest is kind of symmetric, but you have to understand that it's symmetric. It's a lot of case-by-case analysis. And then the limit of the three-diagonal operator looks something like this. In one of the cases, it looks something like this. So you get nice limits for the flat pieces, and you can show that the correlations go to 0 outside of the waterfall. At the central point of the waterfall, Q and Q inverse balance each other out, so it's a nice operator. But now, the interesting cases here and there, you get something else. And you get operators like this. So let's look at this operator closely, like this limiting T. So this operator has the domain x belonging to the full integer lattice. But then the coefficients contain q to the 2x, and as x goes to negative infinity, the coefficients explode, which means that at negative infinity, this operator behaves badly. It is so bad that it is actually not self-adjoint as written, but it's also not closable in a unique way. So to close this operator, and remember this theorem when you have spectral projections convergence, they require self-adjoint operators. And if you want to close this operator, there is a one-parameter family of closures here. And this one-parameter family, well, we didn't quite get there, but we got somewhere close to it. Like we found examples in the literature for what in principle, well, one should do. And it looks like it might be that the closure, like which operator you need to get in the limit, might depend on the position where you are in the waterfall. And unless we want to study the waterfall edge, we don't need the spectral analysis at this level, which becomes very complicated. So that at that time, in the vertical slice behavior, where's my waterfall vertical slice? Okay, so here's the vertical slice in the waterfall case. Because we have the exponential concentration that we get by other means, we really don't have to worry about the approach through spectral projections unless we want to understand the interesting situation at the edge. So moving on, what is really interesting, and then where we get the barcode kernel, is the other cross-section where we are looking at the sequence of orange and blue steps along the waterfall. So that sequence is still kind of it's still a random process. It has up steps and down steps, some sequence of up steps and down steps, and we would like to understand the correlation kernel for the joint distribution of the up steps at the lattice scale. So something like this. So for that, Borid and Goren-Reins already had a spectral picture in the transversal direction as well. And I'm going to spare you the details, but basically this other picture relies on another three-diagonal relation for the Kurakov polynomials that also scales to something as q is fixed. So we take a limit as q is fixed, you scale the spectral data, this three-diagonal relation, to some other relation for functions fn. They're unknown, so you have to solve this recurrence where a of x is an explicit coefficient like that. It turns out it's not very hard to diagonalize this thing, so fn could be found. Not sure what the zoom is. Yeah, so fn's could be found explicitly, it turns out that this operator that you need to diagonalize here is somehow behaving too nicely for us. So it's not bad, it's not unbounded, it behaves too nicely. These coefficients, they don't explode at infinity. Rather, as x goes to plus infinity, you have two things downstairs that dominate the top thing. So it really goes to, I'm sorry, if x goes to minus infinity, there are two things downstairs that dominate the numerator. So this rapidly exponentially decays to 0, but if x goes to plus infinity, then this power dominates. So this decays as q to the x at plus infinity. So it's too nice. But the bad news is that you need to inverse this operator because of the transversal structure. It relies on both the operator and its inverse. And the inverse is bad. It's not well defined. Like you cannot invert this relation. Anyway, any suggestions on how to do it are very welcome, because we we are lost. We were lost. We are still lost at how to push through the spectral analysis. Except that, I mean, even if you cannot invert the operator, you still can play with it with the direct operator. So the direct operator is available and it's explicitly diagonalizable. So you can explicitly diagonalize it by a bunch of horrible formulas. But again, it's infinite Q factorials sort of, which are combined into Jacobi theta function. Anyway, but it's an explicit thing, and Jacobi theta function has nice shift relations, and my operator that I need to diagonalize is also relying on shifts of x. So as you shift an x, everything becomes nice, and you can check that these fns satisfy the eigenrelation. Now, if you pretend that the operators are invertible, and if you pretend that everything works well, then you can write down the formula for the density of the upsteps in the barcode. This formula should not be depending on t because the result should be translation invariant. But we have a t here. We also have a q to the minus n when q to the minus n goes to infinity. So this is the term that makes the series problematic. Without this term, basically this is, there are two eigenfunctions divided by the norm, so it's like one, I mean, but here's you have a t and t minus one, so these are actually going to be orthogonal to each other, which means that if you just mentally erase this negative q to the minus n, you will get actually 0 out of the sum. But if you insert this, then the series doesn't even converge. So the series becomes so, you just take a convergence series and you insert something that diverges, then the series doesn't even, like, the terms of the series don't even go to 0. Actually, they alternate. So in the limit as n goes to infinity, these terms will alternate and they will behave as plus c minus c. So the tail of the series is that thing, which somehow, somehow the formula suggests us something. If you look at this closely, you see that once you're in the physics mode of thinking, you say, well, but if I have, this tail of the series, let me just cut the series, because the series is supposed to be, I mean, a convergence series, you can cut at the term 1 million, and then you get, a very good approximation for the sum. So here's the same thing. Like, you cut it somewhere, you should get a good approximation for something, maybe. But there are two ways to cut it. You can either cut it at even numbers or odd numbers, and you get two different answers, two different approximations. It turns out both of them are correct. So in fact, this series, it diverges, but it gives you two different sums. And these two different sums absolutely have a meaning in the original probabilistic system. Namely, what you get in the limit is two different sums, ρ1 and ρ0, which are encoding the density or the probability of the upstep at an even time or an odd time. And the whole process in the barcode becomes too periodic in the limit. It becomes too periodic. And once you do numerics, this too periodic nature of the process checks out at the prelimit. So this is so the right table is when you take the series and even and odd terms and sum them up until something, then you get a perfect two periodicity. Here in the left column, you get kind of prelimit expressions, which are coming from the correlation kernel of the hexagon. And you see that, the convergence is pretty good. And also we check the barcode, we check these densities in the in actual probabilistic simulations. So here is the reason why you would expect this thing to be too periodic. Which again, it's not clear a priori that is going to be too periodic, but in the end, after formulas, after doing the illegal things and the illegal computations with inverting operators, it doesn't make sense. We get some answer that doesn't make sense, but then we put sense in it by truncation, and then we get two densities. Turns out that, first of all, the densities check out against numerics. Second is that here is why you should expect the two-periodic nature. So here is a barcode process, right? It's an orange, blue, orange, blue, orange, blue sequence. But if we look at the pale orange, horizontal lozenges, they live in a double well potential, and at every vertical slice, the number of horizontal lozenges is fixed. So here's, it goes 1, 2, 3, 4, and then it goes to maximum, and then it decays by 1 each time. So what happens is that once you are looking at what happens when you go from one column to the other column, you gain or lose, let's say, gain one extra horizontal lozenge. And this extra horizontal lozenge needs to go somewhere. It's in the double well potential. So it wants to go either in the up plateau or into the down plateau. And once you made a choice for one column, then the next lozenge better does the opposite thing. So the next lozenge could, in principle, stay in the same column. So in that you see in these two blue steps, but it's more likely for the lozenge to go in the opposite direction. So basically this disparity between the two wells forces me to have a two-periodic answer. So to summarize the waterfall part, before we completely shift gears and see more pictures than formulas, here's the complete conjecture. So we have the series that I can augment by, if you want to have joint correlations, not just the density. So the density will be S equals T case here. So if you want the full correlation, you need expressions for different S and T. So for S bigger than T, you do this, which inserts even worse factors here in front, even worse factors that make the series diverge even worse, even more horribly, and then you need to dampen this by multiplying this by a geometric sequence that makes this converge. So it's also conjectural. We don't even have the proof that this thing converges. But numerically it does. After you renormalize like this, then you would need to take even and odd sums. So M is integer in this limit, and then this expression should have a limit. And then S and T are integers, and then the limit will depend on the parity of S and T. And so the full kernel will be two-periodic with a 2x2 block structure. So it is agreeing with simulation and numerics. And we have the right. So to summarize, we have the conjecture that's a very good numerical conjecture that we got through some kind of illegal physics-style computations, but we also proved kind of everything else that is involved in the global limit shape picture. So we explain completely what is the waterfall, where it comes from, and we close a part of the question that was open since the original work of BGR. But there is some kind of open story here. So let's.
Since you're sort of switching topic, can I ask a quick question?
Sure.
I guess my question is the intermediate regime. What if Q goes to 1 but more slowly? Like instead of 1 minus order 1 over n, 1 minus 1 over n to the 0.99, 1/2, whatever. Do we have any ideas there between Q fixed and Q goes to 1?
I would not be. I mean, even what I'm saying is pretty hard, right? So
no, very hard. I'm asking for
that...
sort of to. It's the geometric picture. I'm wondering if it's a situation where like 0.99 is still classical, 1.1 is still a waterfall, and there is some kind of a scale in between, or do we think it's continuous in these like I'm very much asking for
1.1 should be just uniform. Should be. Like whenever Q goes faster to the
I'm 0.9 versus 0.1. I meant the other direction.
0.9, 0.
To sort of to interpolate interpolate
like,
between the waterfall and the classical picture.
Okay, so look at the edge of the waterfall here. So the edge of the waterfall, if everything that I understand about plane partitions makes sense, then the top of the waterfall, like the lozenges in the top, should fluctuate at the scale that is kind of, and does not depend on n. First of all, it does not depend on n. Second, these things will be like at the scale of kind of k log k, where k depends on q. So if q is fixed, then this thing is almost surely finite. But then as you like, first you take the waterfall limit, then you look at the edge waterfall process, then these top things would fluctuate at some log q scale. So they have like linear growth plus a little bit. If you can catch that, it means that these two things will join together at the center. Now
You've answered the question. Thank you.
that would be fun, right? I mean, but otherwise I don't know.
Sorry for abusing my host privilege.
There is something intermediate going on. Of course, that could be. Okay, moving on. So, last 15 minutes, I'm going to show more pictures than say words. So it's a wholly different story, but somehow it might be closer to some of the interests of parts of the community, including physicists, and even the T embedding community would be interested in understanding what is how to take this approach. So it targets another universality principle in lozenge tilings and domino tilings, and also dimers, that the global fluctuations are converging to the Gaussian free field. So here in the sample, we take two different samples of the hexagon tiling, take the height function, and take the difference. Because the answer is Gaussian, I mean, that's kind of posterior knowledge, but because the answer is Gaussian, you can just subtract the two independent samples, get the Gaussian back. And what you see is that the fluctuations grow at the logarithmic scale and converge to some object called the Gaussian free field that is not even a function, but it's a random generalized function that, well, for this example, the difference of the height functions takes 5 values, -2, maybe 6, -3, -2, -1, 0, 1, 2, 3. 0, 1, 2, right? So it's like not a lot. If you look at the height difference field from the top, you see kind of cluster. You see islands of red, islands of blue, and the islands are macroscopic. So basically, the Gaussian free field encodes the structure of macroscopic fluctuations of a random surface around the mean. Now, you can also do the same story with domino tilings, meaning you take 3D surfaces that are not made out of boxes, but rather made out of plaquettes of a different shape, and you can kind of glue them together and recognize the familiar domino tiling picture. And then in the domino tilings, you still see Arctic Circle phenomenon, and then if you take the same height difference field, you see the same kind of at the level of what you would get is still going to be some kind of a Gaussian free field. Now here, if you zoom in, you see the origin of the process comes from square grid versus triangle grid for lozenges, but the answer is, as you take the scaling limit, is still going to be universal. It's still going to be the same generalized function that lives on the multifractal scale and has, islands of all colors. And it turns out that in recently, in last year, there's been a few works putting random environment behind domino tiling. So it's somehow it works. I mean, it's been worked out for domino tilings in several scenarios and several aspects, and that's why I'm shifting from lozenges to dominoes. But of course, the phenomena and the whole universality and breaking universality of global fluctuations should work for lozenge tilings as well. But in the domino tilings, kind of there are some features that allow you to take different to get the results of the asymptotics. So the most kind of the easiest random environment is what we did with Buffetov and Zographos, is when you take independent weights and put them in a layered manner. So your whole environment is a one-dimensional collection of independent random variables, and then you weigh each tiling or each dimer covering by the product of the weights. So all the weights that are not marked by W are equal to 1. And so this, this particular dimer covering has weight W1 squared, W2 to the power 2, and so on. So you just get kind of, and W's are independent, and they can be any, they can have any positive distribution within reason. And what we found is that you can get Gaussian fluctuations if your variance of the environment goes kind of, so the critical scale is 1 over m. If it goes to 0 faster, you get pure Gaussian free field. If it goes exactly at the critical scale, you get Gaussian free field plus Brownian motion, where Brownian motion is the contribution from the weight fluctuations. Or another interesting case is when you have a fixed distribution of the environment, then you get limit shape of the of the domino tiling will change, and the Brownian fluctuations, they live at the scale of square root of m. The Brownian kills the Gaussian free field, so you don't see the Gaussian free field anymore. So this is the tiling with fixed distribution. And what you see is basically that you still see kind of a domino tiling picture. You still see the limit shape, but the limit shape looks like it's put on the background of a random walk. So that's what it is. I'm just going to highlight another thing that you can also put other weights in domino tilings. You get something looks like a waterfall. Again, it's a conjecture thing. Something probably I'll have to skip. Also skip the methods. Just going to show some pictures. So this is a limit shape. By putting different weights, we also can. So the limit shape is completely characterized by the equation coming from analysis of moments of the distributions. We can get limit shapes that are doing some weird things. So for example, if you take weights which are random and uniformly random in continuous uniform distribution from 0 to 2, you get the limit shape of dominoes kind of touching the corner, which is unusual. Otherwise, you can get something more traditional if you take discrete random variables. So let me show you just a few pictures. So in the random environment, you can either. So what are these pictures? So I showed you the Gaussian free field fluctuations. What did I do? I took two different height functions, which are sampled independently, and there are two pictures here that you see. One is quenched, that's on the right side. One is annealed on the left side. So these two pictures differ by the environment. So in the right-hand side, I take the same environment and take two different samples and then take the difference. And the left-hand side, I take two different environments, and then take two different samples and take their and subtract them. So in the left-hand side, kind of the noise from the environment dominates. You see the Brownian picture, like the Brownian picture in one direction smeared across for the whole picture. And the limit shape is the same. Limit shape on the left and on the right is the same. But on the right, you see a much cleaner. So on the right, basically, you see the Gaussian free field. So this is how the Gaussian free field looks like. It has a size of 1,000. So you really don't see the square picture anymore. You really see the kind of fractal islands of different colors. If you zoom in, you get the lattice, but if you zoom out, lattice is forgotten. You get that kind of thing. Of course, something more bizarre happens in the corner. So the answer here for the corner is that you just need a bigger size to see the same kind of Gaussian free field. Even if it's rippled, the ripples are not going to matter. Not going to matter. So Zographos proved that in a quenched regime you get the Gaussian free field. What we proved is the Brownian motion on the picture on the left. Okay, two more pictures. So maybe advertising some other results. So Toninelli and Muller studied a different layered disorder. So in their work, the disorder, meaning the random weights, were attached not in a diagonal way, but you just rotate the disorder by 45 degrees. You get something very different. So the samples, if you take strictly periodic, meaning these are non-random periodic collection of weights 0.3 and 5 in an even odd periodic manner, then a sample looks like this, which is a gas, which is a kind of a 2x2 periodic domino tilings with a gas phase that's been studied since Chita and Johansson. If you randomize this, meaning you put them in a randomly with probability 2, you kind of have something like that, which is looking different. This is a completely open problem because this Toninelli Muller only studied the torus, and they showed some decay of the correlations, which is not covered by anything that we know from the non-random environment. And so here's the same kind of set of pictures in the Muller-Toninelli. On the left, it looks like Brownian still, kind of. On the right, it looks bizarre. There are two Gaussian free field islands with something in between that is interesting. So you see, it kind of shows you like this island shows you that that the height difference. There is this island where the two height functions differ by +1, but on a very big region. And then here you see difference of negative difference on a macroscopic region. So anyway, so this is, you have to tune the parameters. You have to take pretty extreme Bernoulli distribution with large variance. You get a beauty like that. Then again, back to like, is this waterfall that you see in the middle? It's definitely not a waterfall, but you see some kind of a feature of something that looks like maybe, again, one-dimensional phenomenon happening here, which is interesting. Anyway, so and then there is just, I'm going to just advertise one more set of pictures, one more work. When you take, so this work is by Maurice Dutz and Roger Van Pesky, also from 2025. When you take every edge in the dimer lattice to be random with gamma distribution, and it turns out this choice is integrable, depending on the parameters, you get different samples. So let's go back to my pictures. So now the weird part is that the annealed looks like Gaussian free field to me. So this is this is a choice of parameters that is rather extreme, but the annealed looks like Gaussian free field maybe, and then these guys, the quenched, look like something entirely different. Looks like that you are getting maybe something GFF-like, but then there are much bigger loops, much bigger islands without any. Anyway, so as you change the parameters, the left and right pictures become more and more similar. So these pictures are quite similar to me already. Okay, finally. So sorry for the digression. I just wanted to show you pictures and to break the universality in a different way. But the main thing we did today with Alisa is to discuss the waterfall. So I showed you one approach how you can get to limiting correlations. That approach is a failed approach, but it doesn't fail to give you the answer, which is good, some kind of a result, but it fails to prove the answer. What we have is a conjecture of a sort that one expression has a limit, and then the other expression has a limit, and we don't know that these limits exist, but we conjecture that they exist and equal to each other. So that's the nature of the conjecture. And our limit, our answer, I call it the answer because it has less parameters and also is cleaner looking. It doesn't depend on the dimension of the hexagon, doesn't depend on where you are inside the waterfall. The correlations are supposed to be universal. And I also discussed the random edge weights. And these are just two different instances of breaking universality. Okay, thank you.
Thank you very much. Again, applause at home, please. And of course, if there are any questions, please feel free to unmute yourself or put them in chat.
Thank you.
I will ask again one question, if I may.
Please go ahead.
Thanks. So how to study these things that you have shown on last slides? When you even showed one without a clear shape, you mentioned Gaussian-free field. Could in any way maybe this be connected to Schramm-Levner evolution, say loop soups or similar phenomena? Or how to study this in general?
Okay, so there are three different works I mentioned, and we study them. I mean, not we, but people study them by different methods. So the easiest, the diagonal disorder, is integrable, meaning you can have explicit generating functions, and then you study their asymptotics to get the results. So this thing is studied on a torus, not in the like this is the Aztec diamond region, but this model was studied on a torus. For the torus, you can get a partition function then depending on the weights, and then you can analyze it asymptotically to get correlations. So the last model is integrable in the sense that it turns out that algebraic structure behind domino tilings, which is so-called shuffling algorithm, that algebraic structure can be connected to random polymers, and then the random polymers are available. Like you can use results for random polymers to say something about this. I mean, I showed you pictures. I didn't formulate any theorems because there are very few theorems here. For example, in this work, Dutzvan-Pesky, they don't explain what happens to the correlations inside. They only prove they only compute and prove the tangent points of the limit shape. So the limit curve has 4 tangent points. They find them, okay, as functions of alpha beta. That's the only thing they do by connecting to polymers. Well, not only, but almost the only things they do. They also study local correlations around the tangent points, which are, let me not get, I mean, there are like some results, but nowhere near explaining what happens here. So that's one thing. The other thing you mentioned is SLE. So SLE is supposed to be related to dimer models and height functions because SLE is supposed to be level lines of the height function, which are these loops, right? As you see, for this example, these loops seem to be living in different scale. So in this, here you have very few large loops, and here, like here at the top, in the like northeast part or the northeast part, yeah, you have like a few extremely large loops, but no medium-sized loops, and then in the southwest part you have a lot of medium-sized loops. And the Gaussian free field on the left, I mean, I'm not claiming it's GFF, but it looks to me like GFF, okay? I've been looking at pictures like that for a long time. So there are like loops at every scale. And here you don't have loops at every scale. You have something very different. So question to you or the audience is what do we know about SLE appearing in random environment? I'm not a specialist in SLE, but this is a natural question one would wonder for like connecting these two stories.
Is it all in dimension 2? What would it look in
dimension
arbitrary dimensions?
Yeah, I don't do arbitrary dimensions. I do dimension 2 because of a lot of reasons, right? So mostly the integrability structures and connections to complex analysis, right?
Okay, thank you.
I mean, just to wildly speculate, there is a question of whether this is just an SLE on a different geometry, where the geometry is random and somehow notices this thing. And the reason that this is happening in different scales is because we need to scale things appropriately based on some kind of a thing, depending. Wildly speculating, but like everything you said is absolutely evidence that it's not SLE on this domain, but it could very much be an SLE with a particular metric in the background to sort of like change. I shouldn't, I'm speculating at this point. But it's a very interesting question, which I don't know enough about to speculate. If there are no more questions, let's thank the speakers one more time, both Leo and Helena. Thank you very much. And thank everybody for coming to the One World Probability Seminar this semester, and we will see you guys starting back in the fall. Thank you.
Thanks, bye.
Thanks, guys. That was great. I learned a lot. I enjoyed myself. I hope everyone else did too.
Yeah, thanks, Bob.